Next speaker, Professor Katherina von Dichter. The topic of this talk is inequalities involving means in high-dimensional spaces. Please.
So let's start. We start with the motivation. So we had some projects dealing with diameters. And diameter in some normed space, where the norm is given by some unit ball B, is defined as the biggest segment that is contained in some set X. But what do you do if you have a space where you have some C non-symmetric to be the gauge of the space? So then the diameter of some set X with respect to this gauge, so non-symmetric body, can be just like this, defined like the maximum segment with respect to some symmetrization of C. Namely, you can take C minus C half, so the arithmetic mean of the set. But that's not the only way you can deal with it. So if you want to get a just direct definition like in the normed spaces, so just a maximum segment with respect to this body C, then it turns out that it's exactly the same as taking the maximum segment with respect to C intersected with minus C. So you see that if you deal with different gauge bodies, taking different symmetrizations of C, they introduce you different diameters. So we were working on a project together with our partners using the first definitions, while the other group was dealing with the same problem, but given with another definition. So this way, we had obtained different results dealing with different definitions. And so we were thinking like, can we get a bit deeper in the idea of the symmetrizations to understand how they are related and how we can fix this problem to get some unique definitions that is suitable for everybody. And for this, we will start with some basic things, which are the means of numbers. So let's say that you have some two positive real numbers, A and B, and you know that you can relate the means of them using the arithmetic geometric harmonic mean inequality. So you have here the arithmetic mean, the harmonic mean, and also the minimum and the maximum. You can see as two different symmetrizations of it. And they are nicely related by this chain of inequalities. So this is in dimension 1. What about higher dimensions? How can we introduce means in higher dimensions? So we have to think about numbers A and B as segments. For example, you can say about A, which was a positive real number, as some segment from minus A to A. And B will be a segment from minus B to B. Then taking this is exactly like taking the sum of two segments. The first one will be from minus A plus A half to A plus A half, and the second one is the same with B. Then let's remember the other symmetrization. The other symmetrization was a minimum of two numbers. Remember that if you think about A as your segment, then you have exactly here the intersection of two segments. For the maximum, we just take the convex hull of the union of the two segments. Next one, we have the harmonic mean of A and B, which were numbers. So for this, we need to think, how can we check what is the inverse of a set in higher dimensions? So here you have an inverse of a number. If you think about the number as the length of your segment, let's think how we can take the inverse of a segment. So the inverse of the segment is known to be the polar of a set K, and is given as the set of the point X in Rn, such that the scalar product of X with A is less or equal 1 for every point A in the set K. Here you have some examples. Let's start with the easiest example. The easiest example is just taking the polar of a Euclidean ball. Let's say you have a Euclidean ball with radius 2. Then it's clear that the polar will be again a Euclidean ball, but now your radius will be inversed. So now you will get a Euclidean ball of the radius 1/2. And that's why the polar is known to be the inverse of a set. So here you have a simplex, three-dimensional simplex, and you see that the polar of it is again a simplex, but now it's scaled and rotated. And here you have some other nice examples of three-dimensional sets and its polars. So let's think about the polar of the segment. So the polar of a segment from minus a to a will be exactly a new segment that is minus 1 over a to 1 over a. So what about the harmonic mean of the numbers a and b? Okay, we just plug it in, and that's what we get. So in dimension 1, with a segment, it works out good. What about higher dimensions? Let's see how we can generalize the means of numbers to means of sets in higher dimension. So remember, we have for numbers a and b the chain of inequalities for the harmonic, arithmetic, and the minimum maximum. This was done by Fire, and he said that if you have a and b convex sets, then you can just have also relating the means of the numbers a and b by the following chain of inclusions. So you take some sets a and b, and we start with the intersection. For the intersection a and b, this is the corresponding to the minimum of the numbers a and b. This is included in the second symmetrization. Remember that the polar is the inverse of a set. So this second set is exactly the inverse of a plus the inverse of b over 2, and again taking the inverse of it. So this is the harmonic mean of sets a and b. The third one is quite simple. It's just taking the arithmetic mean. So you take a plus b half, and here the plus is just the Minkowski addition. So you take any point a from the set a and b from the set b, and you take the vector sum. And the last one, the maximum, is generalized to the convex hull of a and b. And you have the nice inclusion of all the four symmetrizations. So for the case with numbers a and b, it's known that inequality is holds if and only a and b are equal. And for the higher dimensions, for the inclusions of the symmetrizations of the set, it's not that clear what happens. What we know from Fire is that these symmetrizations are equal to each other if and only if a is equal to b. But what if there exist some optimal inclusions between them? So can we check whether this inclusions is best possible? So is it optimal in a sense? For this, we need to define what means optimal inclusion. So we have sets k and c, and we say that the k is optimally contained in c, and we denote it with inclusion and write out opt. If surely we have that k is contained in c, and also we will not find another smaller escalation of c with a suitable translation such that k is still contained in c. Here on the picture, you have the black set k and the blue set c. And you see that k is optimally contained in c because you cannot find a smaller escalation of c such that k will be still contained in c, even if you allow translations. So if we have two sets, how can we characterize the optimal containment? To do this, we have a nice condition which describes the touching points. So clearly, if we have two sets where we have the optimal containment, we have some common points on the boundary of both of sets. These points we call touching points. And the optimal containment is characterized by some conditions on the number and also location of the touching points. Namely, we have to have enough touching points which are well spread. Well spread meaning that here you have the touching points P1, P2, P3. And at this point, we can find the hyperplanes supporting the set C such that if you take the normal vectors at the point P1, P2, P3 of the hyperplanes, 0 will be contained in the convex hull of these points. And this condition is an if and only if condition. So we have a nice description how we can characterize the optimal containment just by describing a small amount of touching points and their location. So let's remember what we were doing. We were dealing with the symmetrizations. So we were taking a set C, a convex set. Also, we have to take care that 0 is in the interior because we want that the intersection of C and minus C will be non-empty. And now for the set C and minus C, we have this chain of inclusions. And we also were able to prove that the first inclusion between the minimum and the harmonic mean is always optimal, as well as the inclusion between the arithmetic mean and the convex hull. We were also able to show that the inclusion in the middle may be optimal in some cases, but in others is not optimal. So we were trying to describe the case. Here you can see an example where it's not optimal. So for a triangle and its symmetrizations, the harmonic mean is not optimal contained in the arithmetic mean. And this we were able to describe by fixing the center of the set and using some measurements of the symmetry of the set. So we were dealing with the Minkowski symmetry. Minkowski symmetry is a factor which we denote by S of C, where C is your set of convex body, and it's said to be the smallest escalation of your set minus C, such that C is contained in this escalations time minus C with a suitable translation. And also the suitable translation we call the Minkowski center. For sure, the Minkowski center in some cases is not unique, while in others, it's uniquely determined. And then we restrict ourselves to considering the sets with a fixed center, namely the Minkowski center. So we shifted such that the Minkowski center will be exactly the 0. We introduce our factor alpha of C. This factor is exactly the escalation factor of the convex hull, which is needed to have the optimal inclusion between the minimum and the maximum. So we say if the minimum is not optimal contained in the maximum, then we can find a smaller escalation of the maximum such the minimum will be contained now in the maximum. And now we describe all the possible values of the parameter alpha. First, we have to characterize the case where alpha is equal to 1. Alpha is equal to 1 means that the minimum is optimally contained in the maximum. So, can we describe in which cases, when we have a convex set K, we will have the condition that the minimum of K and minus K will be optimally contained in the maximum of K and minus K. And this was done here. So we say that the factor alpha is equal to 1 if and only if we have the following condition. Namely, we have the touching points P and minus P, both belonging to the boundary of our set. And also, we have two parallel hyperplanes supporting our body K, so sandwiching it inside, such that we have that P and minus P are contained on the hyperplanes. So here on the picture, you see an example of a body K where this condition is not fulfilled. So sure, the body K you can sandwich like you want between two parallel hyperplanes, but you will not get the condition that the point P and minus P that belong to the boundary of K also belong to these hyperplanes. So it means that for this body K here, alpha of k is not equal to 1. So it must be really strictly smaller than 1. So let's go on. And here is presented a diagram that shows the region of all possible values of the factor alpha, depending on the symmetry of the set. So the upper bound is trivial, it's just 1, because the minimum is always contained in the maximum. The lower bound is 2 over s plus 1, where s is a symmetry factor. The symmetry factor can get values from 1 until n, and 1 for symmetric cases, and n is the most values it is possible to get, and this is possible if and only if the body, so the set itself, is a simplex. And also, we have the green bound. The green bound is s divided by s squared minus 1. So, and also we can be able to show that the region of this diagram is filled, meaning that for every point from the yellow area, we can find a body K with this given asymmetry and the needed factor alpha. Here, if you see, the lower bound is given by only one unique boundary, but the upper bound is described by two different parts. Namely, you have the breaking point, the big red dot. So we have that depending on the symmetry, we can show that it can happen that the factor alpha is equal to 1 up to some fixed asymmetry, which is exactly phi, so the golden ratio, so 1 plus squared root of 5 over 2. And from then on, the factor alpha is always strictly less than 1 and is actually strictly less than this green boundary. So now let's describe the situation of this red boundary. So the red boundary, meaning that alpha is equal to 1. This is given by this theorem. It says, if the harmonic mean is optimally contained in the arithmetic means, means that alpha factor is 1, then the symmetry must be given, and this must be strictly less than the golden ratio. And also, if you have that the symmetry is exactly the golden ratio, then the set is unique. And it's the pentagon given here. It is one that you see on the screen, and we call it the golden house because it has the shape of the house and its symmetry is the golden ratio. So next, I want to give you some details on the proof. So the proof of it combines some techniques in convex geometry, some optimization problem, and some simple analysis. So let's start with some general set here, which is convex. Let's say this is a convex set K, and also it's centered. Then we have some touching points. These are the touching points of the symmetry. Remember that for the set, you have that the set and the 1 over s times the set is contained in each other, and we have the touching points between the boundaries of both of them. So we collect them. And here, to see it better, we have the big set is our set K, and the smaller set is taking the set, rescaling it, rotating it. So the smaller set is 1 over s times the set K, where s is your symmetry. And the 3 blue dots are the touching points between two the sets. This means that if we have some general set K and we know that it is centered, we always have these touching points between the boundaries, which are here the 3 blue dots. So this is important information for us. Next, we also have the opposing points of the 3 blue dots, which are contained in the boundaries of the bigger set. So now we have a collection of 6 points, which give us the important information. We also want to describe the situation when the factor alpha is equal to 1, meaning that we have the conditions that there exist 2 hyperplanes that are parallel and 2 dots minus p and p belong to the boundary of the set, which are here the 2 blue dots, which are contained in the set K and also in the 2 hyperplanes. Now, we can also, at the touching points of the set K, take the supporting hyperplanes, which are here given by these dotted lines. So now you see that we have a big collection of points of set K, which describes its uniqueness. So let's leave behind the set K, and deal only with this configuration of points. So our task is to find the body C, which is the most possible biggest asymmetry value, such that all conditions are fulfilled. So condition 1, it must be centered. Condition 2, the factor alpha must be 1. Meaning that we have this collection of points from the centerness and the condition where you have the 2 supporting hyperplanes. And we say that we have a valid situation if we have this kind of configurations of points which fulfilled the needed condition. So now, from now on, what we do is we try to modify our set by some transformations. So let's say some affine transformations, such that we have still dealing with a valid situation and we do not change the asymmetry factor. So let us see, how can we simplify this general situation? The first thing we do is, let's see again, we have these points, blue points, which are the one up, but not on the dotted segment. These touching points were the boundary points of our set. So what we can do, we know that the corresponding blue point on the other side with respect to the center, so this point, lies on this dotted segment, which was the supporting hyperplane. So we can shift it above such that it will still belong to this dotted segment. And by doing this, the corresponding other blue point will be shifted in the direction towards the vertical hyperplane. Same way we do with this point, and then the corresponding this point will be going to the direction of the vertical hyperplane. We were able to show that these 2 points will reach the vertical hyperplanes before these 2 down points will reach it. In this way, we can make this transformation. So now we have that this point and this point, this was the symmetry point of our sets, both belong also to this parallel hypertenuous hyperplanes. And we are still in a valid situation. What is the next step we can do to simplify our set? We can now do the following transformation. So we have that this point up belongs to this supporting hyperplane up, and we can now rescale it. So if we rescale this point, the opposing point will be also rescaled, and we can rescale it until it will lie on the segment connecting these 2 points. Why is it important for us? Because we know that this point, and this point, all 3 must be belonging to on the boundary of the set K, and the set K is convex. And this way we can make this transformation. So let's see what we can do as the next step. Well, we have also these 2 points. And what we do is we modify our set like this. So we have the blue points on the vertical line. We have the blue points on this dotted segment here. So now we keep the segment in a way that until these 2 points will belong to it. And the other thing we do is on the opposite side, dealing with these 2 points. By doing this, we can also make sure that we are still staying in a valid situation. And now we have a set with a boundary point, which looks like this. So we have that these 2 points belong to the intersection of the horizontal segment and the 2 parallel hyperplanes. These 2 points, which are the points P and minus P, belongs also to the vertical segments and the 2 down hyperplanes. And these 2 points, by the definition, lies on these hyperplanes. Well, can we do some other transformations to even further simplify it? The answer is yes. What we do now is we take this point and we move it in the segment which is described by the horizontal hyperplane in a way that where this ray will be passing exactly through the point of intersection of these 2 down hyperplanes, which is shown here. So this is the situation that we are now in. And here I also gave you the notation. So we have the point Q1. This is on the boundary of K. The opposing point minus SQ1 must be also contained in the boundary of K. Then you have Q2, the opposing point minus Q2, Q3 minus Q3. Then you have these 2 points, which are not noted as the points minus P and P. And also the orange dot is the intersection of these 2 hyperplanes. And we have this condition that the linear hull of this minus SQ1 is passing through the point D1. So here in this situation, now it's really clear how to describe whether we are still in a valid situation or not. So now let's think about what happens if we allow the factor S to become bigger. If we allow this, then for sure this point is moving downwards until it's reaching the point D1, meaning that we can increase the factor S until it's reaching the point D1. That's why we introduce a parameter gamma that describes us this situation. We say that gamma is described in this way, that minus SQ1 is equal to S gamma D1. So now for sure, if S times gamma is less or equal than 1, then the point minus SQ1 is above the point D. If S times gamma is greater or equal than 1, then the point minus SQ1 is below the point D1, and we are not anymore in a valid situation. And this gives us now the condition for our optimization problem. What we do, we introduce the points. So now we can really describe the coordinates of all these points, calculate, for example, the points minus P and P, the Q1, Q2, Q3, and so on. And now we collect all this information. So our optimization problem is like this. We have that we are finding the maximum possible value of S, so our symmetry, such that S times gamma is less or equal than 1. Then we remember that we have defined gamma in this way, that minus gamma D1 is contained in the segment minus SQ1 minus SQ3. We remember that we calculated these 2 points, minus SQ2 and minus SQ3, which are given by these coordinates. So we can plug it in. So we have that minus gamma D1 is contained in the segment, meaning that we can describe this point as the combination of the 2 endpoints of the segments. By doing this, we get the gamma as an expression where we have S and A in this way. Then we can take this description of gamma and plug it in our condition s times gamma is less than or equal than 1, which is done in the next line. So our optimization problem reads like this. We are now checking for the maximum s such that this quadratic expression is less than or equal than 1. We can rewrite this quadratic expression to make it a bit easier. This was done in the next line. And we see that this can be solved, namely uniquely. And here you have that s is then given by this expression. Here you still have the parameter a, so you say that this s of a. Then we can analyze this and check how it behaves in a, and we find that this function is increasing in a, meaning that it gets its maximum value for the maximum possible value of a, which is 1. That way, we were able to show that the maximum of s is reached exactly as a point s of 1. So when a is equal to 1. And if we plug in a equal to 1 to this expression in the line above and it simplifies this expression, we obtain the factor 1 plus square root of 5 over 2, which is exactly the golden ratio. So doing all these complicated steps, we were able now to show that the maximum possible asymmetry value for which the parameter alpha is 1 is a golden ratio. And the next thing we were able to do is let's describe the equality case. So now we say let S to be the maximum possible, so the golden ratio. What is the shape of the set fulfilling it? And it turns out this is exactly this pentagon. So if you think here, for example, so this shape remembers us exactly the shape of the golden house. And if you have the equality condition, you have minus s times gamma is exactly this point. So the shape of the body is given exactly by this boundary segments. And it's this kind of pentagon. And this body is unique. So I also wanted to share with you another result that is not really connected to it, which is the side result, but it's really beautiful by its own. So this was some fact that we were checking to be able to prove some technical lemmas, but the result itself is really beautiful. So it says, if we have some planar set K, which is centered, and also with quite high asymmetry, so it looks something similar like a simplex, like here you have this yellow set K, then we can describe how will be the intersection of the boundary of the set K and minus K. Namely, in this case, the number of intersection points of the boundary of K and the boundary of minus K will be exactly 6. So this is quite interesting, and I'm not sure if anybody came across this before in the literature. If yes, it will be really interesting to find literature about this, like reading about this. If not, I think it will be some useful technique, probably also for people which are coming from other areas than the like convex geometry itself. So again,
5 minutes late. 5 minutes left.
Okay, thank you. So that's actually everything. Thank you for your attention. And that's it.
Okay, thank you very much for this presentation,
Thank you.
Professor.